have three really interesting presentations on things that are happening with 8K. Not surprisingly, we have three people from NHK where we have basically an 8K incubator. I like to call them the skunk works of 8K because they're doing so many cool things. So I'm going to introduce our first speaker, who is Shingo Sato. He joined NHK where he worked on the creation of news programs immediately after graduating from Waseda University. And in 2015, moved to the technical management section of NHK, has been in charge of development of camera systems for TV studios, especially for 8K, which is quite a challenge. So what he's going to talk about today is something I think you really want to pay attention to do. It could be the next generation of camera sensors. It is an 8K camera using an organic photoconductive film to boost the sensitivity of camera sensors, which, given the challenges we have with making camera sensors with 8K worth of pixels, trying to get enough light through them, try to be able to write the data to a AD converter, and then working with different lenses, we need more light. So, Shingo, I invite you to the podium, and you'll explain in greater detail what's going on with this organic photoconductive film later. Shingo Sato.
Thank you for your introduction. Good morning, everyone. Ohayou gozaimasu. I'm Shingo Sato from Japan. I work for Japan Broadcasting Corporation NHK. To date, NHK has developed a variety of cameras to support the production of 8K program in a wide range of genres. This time, we developed an 8K camera recorder using an Organic CMOS image sensor, and it supports rotating shootings. Today, I'd like to talk to you about the design overview of this camera. This is outline of my presentation. First, in introduction, I will explain the 8K broadcasting in Japan, and then I will explain the background to the development of this camera. After that, I will explain the configuration of this camera. Next, I will talk about the camera head unit. In this part, I will explain the technologies for increasing the dynamic range and the effect of the high dynamic range. Next, I will talk about the recording unit. In this part, I will explain the function of the recording unit and improve the workflow. After that, I will explain about performance and the specifications. Finally, I will talk about conclusion. Let me start from the introduction. First, I will talk about 8K Super High Vision in Japan. NHK started test broadcast of 8K Super High Vision on August 1st, 2016. And we started the regular broadcast of 8K Super High Vision on December 1st, 2018. Furthermore, the Tokyo Olympics will be held in 2020, and the Osaka Expo will be held in 2025. In order to broadcast this event, NHK is developing 8K equipment to expand 8K broadcast content. I will talk about the parameters of 8K broadcasting. The number of pixels is 16 times that of 2K, and it is a super high definition video. The color gamut is wider than before, and it covers 99% on pointer colors in the database of object surface colors. The luminance dynamic range is also wider. Thanks to that, faithfully reproduce technically challenging scenes of daylight and shadow, metallic reflections, and other scenes with great variations between light and dark. The 8K broadcast in Japan use hybrid log gamma for high dynamic range, which has been recommended in ITU R-Rec BT2100. In addition, the bit depth increases to 12 bits, the frame rate can be up to 120 frames per second, and the sound can be up to 22.2 channels. I will talk about NHK broadcasting. NHK produces a wide range of content: news, dramas, sports, nature programs, science programs, and educational programs. Supporting program production over a wide range of genres requires compact mobile cameras with integrated storage for location shoot, in addition to system cameras that requires camera control unit. With such an integrated camera, in order to capture high-quality video in outdoor environment with strong contrast ratio between light and dark areas, 8K cameras must have higher dynamic range. And to meet this requirement, each pixel in the image sensor should be able to handle more single volume. With a shift to 8K, the CMOS image sensors used by existing cameras are limited with regard to their dynamic range due to their small pixel size. In addition, for rotating shootings, it is necessary to be able to record for longer times. However, 8K recording has a large amount of data. Therefore, there is a problem that the recording time is limited. In addition, it is necessary to be able to confirm HDR and high color gamut look on site. Production teams have demanded an 8K camera that would solve these problems and support a workflow. This is as efficient as one for HDTV location shooting. This time, we developed a new 8K camera to solve these two problems. Next, I will explain the overview of system configuration. It is a photograph of a camera and a configuration diagram. It has the same structure as a conventional broadcast location camera and aims to maintain the same feel as before. This camera consists of a camera head unit and a recording unit. The head unit uses an ordinary Super 35mm optical system that is widely adopted in the field of digital cinema in order to use commercially available lenses for digital cinema and to achieve 8K resolution easily because of the large pixel size. Two optical filter turrets are installed. The first one has a clear filter and 3 types of ND filter. And the second one has a cap filter and CC filters that supports 3 levels of color temperature. The CMOS image sensor with 7,618 times 4,320 pixels uses an organic thin film sensor as the optoelectric conversion part. The image signal from the camera head unit are output without processing as individual color channels green 1, green 2, blue, and red. Record unit has a HQX codec and 8K signal process. After the image signals pass through the camera's internal signal processing, it is converted to luminance and chrominance signals encoded as compressed HQX and stored on a SSD. As I mentioned earlier, an organic CMOS image sensor is used. By using this sensor, a high dynamic range is achieved. I will explain the mechanism later. Next, I will talk about the camera head unit. I will talk about technologies to expand the dynamic range. A number of technologies have been proposed for increasing the dynamic range of cameras. A typical method is to combine images with lengthened and shortened exposure time. These technologies can yield extremely high dynamic ranges by increasing the variation between long and short exposure times. But with subjects in motion, this method can produce image blur due to the variations in the timing of the shooting. Next, a method is to arrange 2 large and small photodiodes in 1 pixel and combine them, varying the quantity of exposed light by splitting the photodiodes that make up individual pixels into large and small pixels, has been proposed as another way to expand the dynamic range. Given the need to sample the image at different locations, this approach is happen to superior resolution. The two methods just introduced have disadvantage in image quality. For this reason, we decided that it would be difficult to adopt it for TV cameras. The most effective technologies for expanding the dynamic range without diminishing image quality is to increase the charge electron during exposure in one frame. Image devices using organic thin films, which have been the subject of recent research, are known to have a higher saturation charge. This time, we adopted an organic device. I will explain the mechanism of an organic CMOS image sensor. Figure shows the structure of a conventional CMOS image sensor and an organic CMOS image sensor. A backside illumination silicon image sensor, BSI sensor, consists of a photodiode which functions as an optoelectronic converter and floating diffusion which release and accumulate the signal charge. Both the photodiode and floating diffusion appear on the same silicon substructure, and this arrangement limits the area available to the floating diffusion. Thus, it is difficult to increase the saturation charge. Conversely, an organic CMOS image sensor stacks the organic thin film, which functions as optoelectronic converter, on top of the silicon substrate in an area independent of the floating diffusion. This allows the light gathering surface area to expand without being constrained and for the floating diffusion to be enlarged, so that the saturation charge can be increased. The sensor design is otherwise largely unchanged, and the saturation charge is increased, and high dynamic range is achieved. In this development, we try to increase the camera's dynamic range by using an organic CMOS sensor. I will talk about effect of high dynamic range on camera design. For the conclusion, increasing the image sensor's dynamic range allows a wider setting for the camera's sensitivity and dynamic range. With conventional 8K cameras, noise is a problem, so we want to use a negative gain. But when we use negative gain, the dynamic range reduces. In this camera, without reducing the dynamic range, SNR is improved by using a negative gain. This is because the sensor has a high saturation charge. I will explain the principle after the next slide. First, I will explain the signal flow. In the camera head unit, the charge accumulated in the signal pixel floating diffusion is amplified by the analog gain and then converted from analog to digital to output a 14-bit digital signal. This 14-bit digital signal is then subjected to gamma and knee correction and is finally output as the image signal. By defining how much accumulated charge represents 100% white, which means decides digital gain, we can specifically determine the dynamic range, sensitivity, and SNR. Here, the dynamic range is defined by the overexposure headroom, and the sensitivity is defined by the F number. Next, I will explain the relationship between headroom, noise, sensitivity, and digital gain. The relationship between the camera's headroom and digital gain is proportional as shown in the figure. Therefore, it can be set higher by increasing the digital gain. Similarly, noise and digital gain are proportional, and F number and digital gain are proportional to the square root. Therefore, for example, when the camera gain setting is lowered, the headroom and sensitivity are lowered, but the noise can be reduced. However, if the gain setting is lowered with a normal sensor, having a small amount of saturation charge, the dynamic range is rarely reduced. I will explain the principle in the next slide. The graph on the left shows a normal saturation charge sensor. The graph on the right shows the sufficient saturation charge sensor. The black part of the figure indicates the noise level. The gain here indicates an analog gain after sensor output. Consider the case of the normal image sensor when the maximum saturation charge at an analog gain of 0 dB is assigned to a full 14-bit signal. If we apply a negative gain, the noise level drops as shown in the figure, but the entire 14-bit of output cores cannot be used and the headroom is lost. It becomes impossible to maintain a 400% headroom, and we can only output up to 200%. Conversely, the case of sufficient saturation charge sensor, applying a negative gain cuts the noise level, and we can still freely accept the saturation charge. Thus, none of the range represented by the 14-bit is lost, and the output can reach up to 400%. To summarize, this is one way to reduce noise without loss at the headroom. Next, I will talk about SNR with respect to photonic shot noise. That is improved by the effect of negative gain using an organic CMOS sensor. Ordinarily, for the same optical format, increasing the pixel count reduces the pixel size. With an 8K resolution, the pixel size in a super 35mm sensor is approximately 3 micrometer. As the pixel size decreases, the sensitivity decreases accordingly. In order to increase the sensitivity, it is necessary to use gain up, which increases the impact of photonic shot noise. How can we reduce the impact of photonic shot noise? Figure illustrates the relationship between incident light charge pixel and photonic shot noise. The horizontal axis represents the amount of incident light, and the vertical axis represents the amount of charge pixel by generated and the amount of photonic shot noise. S2 requires more incident light to be 100% white, and in this case, a lower camera gain is set. In the example shown in figure, S1 is at 0 dB and S2 is at minus 12 dB. Whereas the relationship between the charge pixel and incident light is proportional, the relationship between the photonic shot noise and the incident light is proportional to square root. Formula for SNR calculation are shown on the right. In the formula, S2 with negative gain is higher SNR. The organic CMOS image sensor allows the gain to be lowered to minus 12 dB without reducing the headroom. As a result, the SNR with respect to the photonic shot noise is increased by 6 dB as shown above. This is a talk about the dynamic range of the camera head unit. Next, I will talk about the recording unit. First, I will explain the functions of AK recording unit. It's a main function of AK recording unit. The recording unit of the camera has a function that devalues the signal sent from the shooting unit. Equipped with a codec that compresses with HQX, we establish a workflow that allows cameramen to check HDR and wide color gamut images while recording. By setting the average compression rate of the HQX codecs to about 1/7, it is possible to maintain high quality with almost no apparent deterioration. In addition, a function to generate HDTV proxy video at the same time is added. I will be described later in the workflow improvement in HDTV proxy video generation. Next, I will explain the storage media. We use an SSD package dedicated to 8K video data storage. Each commercialized SSD with a maximum storage capacity of 4 terabyte and an average compression rate of 1/7 for HQX coding can record about 40 minutes of video. In the workflow described below, we store the proxy files separately on readily available SD card instead of the SSD to allow the work to proceed in parallel. I will explain the input and output interface. The recording unit also has a HQX decoder which can playback 8K video recorded. The output interface adopts 12G SDI quad link, and when we have an 8K monitor, we can check the 8K video in real time at the shooting site. HDTV monitor output is also provided. In addition, a multi-channel audio digital interface input is provided to allow 22.2 channel audio to be recorded along with video. And also, timecode input-output and remote control terminals are provided. I will explain the workflow. Current 8K location cameras record compressed raw files in the field. The monitoring environment on location is a simplified one using SDR2K images. HDR and wide color gamut can only be accessed after file importing and debayering, as the parameters cannot be checked during shooting. And files need to be ingested and turned into editable material at the station after the shoot. And uncompressed 8K data is very large, and data rate is about 48 gigabps. The post-production workflow has a problem in processing time, copying time, storage capacity, and so on. Thus, it is difficult to directly edit 8K video. Although offline editing using proxy file is an effective way to resolve these issues, but generating the proxy data from the massive 8K files is a time-consuming process. So it is required to generate a proxy file at the location. I will explain the improved 8K workflow. The proxy data stored on the SD card is converted to the H.264 format, which many nonlinear editors can easily handle. Using the EDL and AAF editing data generated at the time, it is possible to work more efficiently up to the rough edit phase by relinking to the original 8K files on an 8K online editor. I will talk about the look of location production. In programs such as Dramas, it is ideal for the video engineers and director to have the same final look in mind throughout the making process. In conventional workflow, it is necessary for video to be ingested at the broadcast station after the location work finish, and it is necessary for video engineers and the director to supervise for both the location site and the broadcast station. Furthermore, grading work after that was difficult. The workflow we developed, which allows the look of editable material to be shared on location site between the video engineer and director, has the potential to dramatically improve the efficiency of post-production work. This is a talk of the recording unit and the workflow. I will explain the performance and the specifications. The table shows the performance and the specifications of the camera head unit. The weight reduced to 3 kilograms. Power consumption is low at 43 watt, so it is suitable for the location. Use of an organic CMOS image sensor permits a headroom of 400% or more, even with negative gain. The sensitivity and SNR when gain is at 0 dB are the same as those of conventional CMOS 8K systems. Thus, in outdoor shootings with sufficient light using negative gain, enable the shoot of high-quality video with good SNR. The table shows the performance and the specifications of recording unit. Weight is 4 kg and power consumption is 75 watt. In terms of the performance of the HQX codecs, setting the compression ratio to 1/7 ensures that nearly all scenes are captured at the peak SNR of 40 dB or better when using reference 8K moving picture sequences. In addition, this time we adopted an organic CMOS sensor. As a feature of an organic CMOS image sensor, a variable ND function can be implemented by controlling the voltage applied to the organic thin film. Such controlling voltage can also be used for global shutter function. We plan to implement these functions further in the future. I will give a conclusion. We developed an 8K camera using an organic CMOS image sensor to meet the needs of a broadcast 8K camera in terms of specifications and workflow efficiency. Ensuring a wider dynamic range provided more freedom in setting the camera's level diagram to permit a wider range of visual expression. This camera can also record in RAW, but with the development of an HQX recorder, options have expanded and an efficient workflow has been realized. This newly developed camera is used for 8K broadcast program production. Using this camera, we will mass produce the highest quality 8K programs that no one has ever seen. ありがとうございました。